We're going to take a look at problems 9 and 10 on the projectiles launched at angles review now. In number 9, there's an airplane, and it's diving at an angle of 37 degrees below the horizontal. So you can see there 37 is below our horizontal line of velocity in the x direction. It's going to release a projectile at an altitude of 730 meters, so 730 meters above the ground. So you can see that our y displacement is negative 730 because that's how far down it's going to go. The projectile hits the ground 5 seconds after being released, so we actually have time in this problem. So we have time in both the x and the y. What is the speed of the aircraft? How far did the projectile travel horizontally during its flight? And what were the vertical and horizontal components of the projectile's velocity as it strikes the ground? So we have a couple things that we're going to need to find here. In the speed of the aircraft, what we're going to ultimately do in finding the speed of the aircraft, we're looking for this hypotenuse. So we would need the velocity in the x direction and the initial velocity in the y direction. We don't know that information right away, but we can find some of that stuff out because we have certain pieces of information. For example, in the y, we know the time. We know the acceleration is negative 9.8. We know the displacement is negative 730. What we can do is solve for the initial velocity here in the y direction, which would get us this side of this triangle, by using the third equation, d equals v naught t plus 1/2 at squared. Rearranging that for v naught, we would get this equation here. How did we do it? We subtracted the 1/2 at squared over to the left side, which is why we have d minus 1/2 at squared. And then to get the v naught by itself, we divide by time, which is why time is in our denominator. We plug in our numbers. D is negative 730 minus 1/2 a, negative 9.8. T is 5 seconds squared divided by 5 seconds. And that's going to give us an initial velocity of negative 121.5 meters per second, which makes sense because it's downward. So it should be a negative 121 in this case. Now to find our velocity in the x direction, which we can do, we now have our opposite side of this triangle. We have our angle, which is 37 degrees. So I would use a little bit of tangent in order to solve for the velocity in the x, because tangent of 37 is my opposite, vy, over my adjacent vx. So when I rearrange that to solve for my adjacent vx, I would have the opposite side divided by tangent of 37 gets me my velocity in the x, which is 161.2, which is one of the things that we were trying to find. That's going to let us find the speed of the aircraft at the time that it released the projectile, because we now know our velocity in the x, we know our velocity in the y. We can do a little Pythagorean theorem, which is our hypotenuse equals the square root of both legs squared. So 161.2 squared plus negative 121.5 squared. And once that comes out of the square root, we get a velocity of 201.9 meters per second. Solving for how far in the x direction the projectile traveled, we have our velocity in the x. We solved that previously at 161.2. We know the time is 5 seconds. So very simply, distance equals velocity multiplied by time in the x direction. Velocity of 161.2 multiplied by 5 seconds tells me in the x direction it travels 806 meters. Now, when it looks for the velocity components as it strikes the ground, the x component never changes because the x velocity never changes. So ultimately what we're finding here is final velocity in the y direction. To do that, vf equals v naught plus at. We solved for v naught earlier as negative 121.5, a is negative 9.8, and time is 5 seconds. We don't have to do any algebra here. We just plug into our calculator, and we get the final velocity in the y direction is down negative 170.5 meters per second. Moving on to number 10, there's a construction site, and there's a worker on the 3rd floor that's going to be tossing. They're going to be tossing some tools to another worker on the ground 13 meters below. Assuming that the worker throws the tools with an initial velocity of 4 meters per second at an angle of 68 degrees below the horizontal, how far from the base of the building do the tools land? So here's our picture. Here's our person up on the 3rd floor. They're going to be tossing something downward at an angle at 4 meters per second. The angle here is 68 degrees below the horizontal. The velocity in the x we're not sure of, and the velocity in the y we're not sure of, but we can solve for both of those using our SOHCAHTOA. Velocity in the x equals cosine 68 times 4 meters per second. So we know our x velocity is 1.5 meters per second, and that's written right here on our x column. In the y direction, it's still the opposite side. So we're going to use sine of 68 times 4, which is going to get us 3.7 meters per second. But realize this is downward. So when we plug it into our y column, we have to make sure we put negative 3.7 seconds. The person below is 13 meters lower, so our displacement is negative 13, and our acceleration is negative 9.8. To solve for how far this thing is going to go in the x direction, we would need time. So we're going to solve for time in the y direction because we have 3 pieces of information. So we can use this third equation, d equals v naught t plus 1/2 at squared. Using the quadratic formula for this equation, negative v naught plus or minus square root of v naught squared plus 2ad all over a. I can plug in my numbers. Negative v naught, well, it's negative 3.7, so that's why this is positive out here. Plus or minus the square root of negative 3.7 squared, plus 2 times the acceleration, negative 9.8, times d, which is negative 13, all divided by negative 9.8. That gives us 2 possible times, 1.3 seconds or 2.0 seconds. We're obviously going to use the 1.3 because negative time doesn't make any sense. So to solve for how far this goes in the x direction, I take my x velocity, 1.5, multiply by our time, 1.3, to get a distance in the x direction of 1.95 meters.